The Realistic Skin Model, or RSM, in ASAP is a useful tool for generating biologically accurate optical tissue models of human skin. What sets the RSM in ASAP apart from other skin models in optical software is the ability for the user to specify source wavelength with a range of 250 to 1,000 nanometers, and the ability to manipulate optically relevant molecular concentrations to model disease states in skin models. Now, what we see here is an example of such a skin model. We have a 3-layer model: the stratum corneum, the epidermis, and a bulk dermal layer. And we can see, as a 560 nanometer wavelength source is traced into the system, the scatter properties of that system. Now, if we take a look at this same trace in a 2-dimensional plot, what we can examine is the specular and diffuse reflectance from this trace, and we can see that several rays have not only directly reflected off of the surface of the skin, but also entered the skin, scattered, and then escaped back through the surface. And this information can be relevant in sensing applications and imaging applications. If we return to our 3-dimensional model, then we can take a look at how we can track the energy in this model using a voxel system. And this is fluence tracked as a function of all 3 dimensions in the same trace, 560 nanometer wavelength source. Now let's compare this to a same trace with tracking absorption in the skin. And we can see that there's a marked difference between the energy absorbed in the skin and the amount of energy flowing through the skin, or the fluence in the skin. Other ways to visualize such energy are provided in ASAP through plots such as an isometric plot. And this is an isometric plot of the fluence that we were just examining. And you can see a very gradual fall off in energy. Similarly, in a contour plot, we can look at fluence as a function of depth, and we can see deep penetration within the skin for energy. Now, comparing those to the absorption plots, we can see a high confinement of energy in the epidermis, and then a steep drop-off and fairly lower absorption in the dermal layer. And this is reflected in the contour plot. In fact, so much so that the energy that's absorbed within the dermis is beyond the bounds of our scale for this particular contour plot. Again, looking at the same information in a different manner, we can visualize the fluence in the skin in a pictorial representation and examine in the Z and X dimensions the fluence throughout the skin model. And we can see a gradual decline in energy and a gradual, or a rather steep drop off on either edge, but a gradual rounding of the source as it propagates through the system. Now, comparing this once again with absorption, we can see a dramatic drop-off as we reach the dermal and epidermal junction, and then rather low absorption throughout the dermis, with a similar profile in the X dimension. Now let's examine how we would model this example file using the RSM dialogues. The first dialog that we see is a realistic skin model initialization dialog, where we can specify options such as the sample surface area and the wavelength. The wavelength is incredibly important to the realistic skin modeling system in that it allows us to set the optical properties of the skin for this particular wavelength. We will check off the Use Default Material Parameters box. If we use the default material parameters, the RSM is preloaded with variables that are taken from published literature and would give you a generalized skin model that's useful in many situations. However, in light of the fact that we are examining particular chromophore concentrations in the skin, we want to not use default parameters and instead look at specifics of the skin. We will use the default source and perform dialogue-driven analysis. The realistic skin model provides 3 methods for model creation. Visual characteristics, which, if the quantities are unknown for chromophore concentrations or specific optical properties such as absorption and scatter, then we can use the visual characteristics of the skin, the lightness or darkness of the skin, say, to qualitatively specify a skin model that may be useful in certain situations. We can also specify our skin model using chromophore concentrations, which is a direct method of controlling the exact concentration of light-absorbing molecules in the skin. Our third option, direct entry, allows us to measure skin within a lab environment and then take those measurements, transform them into scatter, absorption, and anisotropy coefficients, and then input those into the RSM to create a virtual tissue that will last even when the real tissue degrades. For this situation, let's take a look at chromophore concentrations. Now, we're provided with the ability to model multiple layers of skin: stratum corneum, epidermis, dermis, hypodermis. For our situation, we looked at the stratum corneum, the epidermis, and the dermis, so we'll use the default values for this. The RSM provides the ability to model both a single-layer bulk approximation to the dermis or a 2-layer papillary and reticular dermal model, which will allow us to look at the interdigitation between the epidermis and the papillary dermis. Our model was a single-layer bulk approximation, and so we will use the default for this as well. The RSM provides several optically relevant and physiologically relevant geometries, such as hair and blood vessel modeling, which we won't examine in this particular model. For each layer modeled, we can examine and change the thickness, the anisotropic scatter coefficient, and the index of refraction. Also, for each layer, there are confined chromophore concentrations, such as beta-carotene and water for the stratum corneum. If we change, say, the volume fraction of water in a particular layer, we can modify that layer to examine states such as dehydration. The epidermis, once again, presents us with the ability to change thickness, the anisotropic scatter coefficient, the index of refraction, as well as chromophores that are specific to the epidermis, such as eumelanin, which is a brown pigment, and pheomelanin, which is a yellowish-red pigment. And the ratio of these two chromophores controls the relative color of the skin, which allows us to model different ethnicities. We can also model, once again, beta-carotene, water, and control the total volume fraction of melanosomes, which, when increased, will darken the skin. In the dermis, we're presented once again with the thickness, anisotropic scatter coefficient, and index of refraction. And in the dermis, we can control the amount of hemoglobin in the blood, which, if we reduce it, can mimic some anemic states, the concentration of beta-carotene, the concentration of bilirubin, which when elevated can cause jaundice and can be optically relevant in certain situations, the volume fraction of water, the volume fraction of oxyhemoglobin, which is a ratio of oxygenated blood to deoxygenated blood. If we control this value, we can also model hypoxic states, and the total volume fraction of blood in the dermis. If we increase this volume fraction, we can model states where a high amount of blood is present in the dermis, such as a high vasculature that can be seen in things such as port wine stains. At this point, the realistic skin model has created both the geometry and the optical properties of the skin, and now we'll proceed to our source creation trace, and analysis. Our default source will be slightly less than the number of rays that we used for the previous trace for expediency. We will randomize our rays and use a total source flux of 10 milliwatts. Our trace options menu also presents us with a wealth of different options, such as the number of pixels, the fluence or absorption tracking in our voxel system. We'll choose fluence. The window of interest, which allows us to examine the voxel system at different views from different perspectives. The area and depth to track in our voxel system. The number of slices in the dimension that we are not viewing in order to get a depth resolution. Plot options, whether or not we would like to visualize none of our geometry or rays, geometry only, or examine both geometry and rays in a full plot, as well as the ability to plot only a subsection of the rays that are being traced. We can also choose the ray color, which in no way impacts the wavelength that we've chosen previously. We will choose green, and now you can see the stratum corneum, epidermis, and dermal layers, as well as the source being traced through the system. And we can see, once again, a high amount of scatter within the system, as well as specular and diffuse reflectance from the surface of the system, and rays that have escaped through the back of the system. These are generally low energy rays and can either be neglected or collected on this dermal surface for analysis later. Now we're presented with the ability to perform analysis via a dialog system. The RSM calculates, based on the number of slices and the size of our analysis region, the spacing between the slices, which will allow us to more accurately select which slices are of importance to us. So, for instance, we will view a single slice that slices through the center of our system, slice 75, and display that single slice. We can also average our information before we display it, and that average is over 1 pixel in every dimension. We can use a logarithmic scale, which we won't do in this particular case. And we have 3 output types, which we've seen before: isometric, contour, and a picture display. Now our 3 display types will look a bit different from the display that we had seen before due to the fact that we traced a lower number of rays. The RSM also provides a method by which we can return to the analysis in order to perform an additional analysis on the same data set. Moving forward, the realistic skin model allows us to output the code for this particular skin model to a file so that we can use it later in a separate optical system. If that optical system is well defined, we can change the position and rotation of the skin model to position that skin model within that optical system before we output it to a file in the X, Y, and Z dimensions for position as well as rotation. Finally, the RSM allows us to either output scatter models only, which would allow the user to apply these scatter models to previously defined geometries, or output both scatter models and geometry, which would create a slab tissue model similar to the one that we've seen before. We can also provide a unique file name for our skin model so that we can easily find it in our working directory. Our model output is complete, and the RSM has finished. Now let's take a look at the output that we've obtained. The name of our model was skinmodel.inr. And it's a complete working INR script that can either be used as is or copied into a separate optical system to be combined with an optical device so that you can examine both an optical system and a biologically relevant tissue phantom simultaneously. So to summarize, what we've seen here is the RSM's ability to create human skin models based on user-defined parameters, such as wavelength and optically relevant molecular concentrations, something that no other optical software tool can do,